Hello, students. Today's class is on based on your alkynes and its preparation and its reaction, and we'll end our hydrocarbon today by seeing also Freadal craft reactions, alkylation, acylation, etc. So let us start from alkynes. Actually, alkyne is very simple. Actually, alkynes. At first, alkynes having free hydrogen with the alkynylic carbon can easily be identified or by Tollens reagent or failing solution. This is because you can see here in case of alkynes, these two hydrogens, so carbons, are sp hybridized. So as they are sp hybridized, their S character is high. S character is 50%. So these carbons are acidic in nature. Sorry, these hydrogens are acidic in nature. So they can be replaced. So as an example, CH triple bond CH, if you give here AgNO3 in presence of NH4OH, this will give you AgC triple bond CAG, and CH triple bond CH, here you can give Cu2Cl2 in presence of NH4OH. This will give CuC triple bond CCu. So these are the two distinguishing test of our alkynes. Actually, this will give a silver precipitate, silver gray precipitate, and this will give you a red PPT. So these are the precipitates that are formed due to the free hydrogens. So as preparation, you can prepare alkynes from carbides. As an example, when calcium carbide react with water, it gives acetylene and calcium hydroxide. So you should also see the structure of calcium carbide. This actually comes in our exam. This is known as calcium carbide, which have, you can also calculate the sigma and pi bonds. Okay, 3 sigma 2 pi bonds is present. 3 sigma 2 pi bond is present. So you can give here water. This will produce CH triple bond CH plus calcium hydroxide. This is ionic carbide. Carbide can be classified into many types: ionic carbide, covalent carbide, and interstitial carbides. So this is a very good example of your calcium carbide. Oh, sorry, ionic carbide. So whenever you give water to calcium carbide, this will also always produce acetylene in presence of calcium hydroxide with the evolution of calcium hydroxide. So this is the uh, general preparation of your acetylene. Then we can also prepare alkynes from vicinal dihalides. As an example, you can see here CH2Cl, single bond CH2Cl. If you give here alcoholic KOH followed by sodamide This will always produce CH triple bond CH. What happens? At first, one hydrogen is removed from this carbon, Cl is removed from this carbon, a double bond forms. Again, NaNH2 affects here. One hydrogen is replaced from here, and Cl will be replaced from here. So we'll see the mechanism here. You can see here. We are seeing the mechanism here. OH minus E2. This occurs in E2. Okay, E2. So CH double bond CH2. Here you can see a Cl. Again, now what happens? Now NH2 minus, as it is a very strong base, it extracts hydrogen from here, bond gets here, and Cl will be removed from here. So the structure is CH triple bond CH. Name is acetyl. So this is the structure or the preparation from vicinal dihalides. Always remember here, you can never use excess alcoholic KOH in place of alcoholic KOH followed by sodamine, because alcoholic KOH is not able to release to extract this hydrogen. Alcoholic KOH is a relatively milder base than NH2 minus. This is a very strong base. That's why it can extract the hydrogen from here, but alcoholic KOH is unable to release the hydrogen from here. So you should always remember, so from the vicinal dihalides, you should always use alcoholic KOH followed by sodamide. Okay. Now, the next one. So these are the general preparations of our alkynes. Okay. Now we will see some reactions. As in our previous class, we have seen the hydrolysis of alkynes. Those who did not see the hydrolysis of alkynes, if they can see the video. Hydrolysis of alkynes, we saw that we should do the hydrolysis. We should do the hydrolysis in presence of Hg2 plus and 20% H2SO4 in presence of HgSO4. We saw that the carbon which has a higher carbocation stability, we will get a double bond O. So those who do not know this, they can see my previous video, CH3. So this is the acetone. How to do this? You can see here, CH3C triple bond CH. OH minus attacks here, bond goes here, it will get the H plus. So the first step is this OH minus double bond CH2. Again, OH minus attacks here, bond goes to here, it will get the H plus, and the structure will be CH3, C, OH. Here it is a OH, here it is a CH3. So one carbon, two OH groups cannot be possible. That's why the structure is CH3, CO, CH3. So you should see my previous video in which hydrolysis of alkynes is done. Actually, in our previous video, we have done the entire hydrolysis procedure of all the organic compounds that are possible in your 11 and 12 syllabus. Okay. So this is the mechanism of hydrolysis or addition of water. Okay. So this is the hydrolysis of or addition of water. Next, we will see the polymerization. We can see there is a special reaction where CH triple bond CH is a red hot Fe tube. This will produce benzene. How to produce benzene here? You can see it is a polymerization reaction. 3 acetylene molecules are required. Now see the mechanism here. This bond goes here. This will attack here. Bond will go here. This will go here. This will go here. And this will go here. So the structure is becoming like that. Now the structure is becoming like that. Here, here, here. Hydrogen, 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 benzene. This is known as the polymerization of your alkyne. Okay, this is the polymerization reaction. This same type of reaction is done by many of the alkynes. As an example, you can see here CH3, C triple bond CH. You can give them red hot iron tube. This will produce sorry CH3, CH3, CH3. This is known as mesitylene. So you should see the mechanism here. You show the mechanism here. This like this goes here, this goes here, this goes here, and this is the product is mesitylene. Again, you can see another mechanism here, another reaction of polymerization. This is 2-butene. Whenever three red hot iron tube. Now you can see the mechanism here. Now what happens? This bond goes here, it will get a minus charge. It will attack here, the carbon valency becomes 5. This bond goes here, valency of here it will be a minus charge. This will attack here, the bond will go here, and this will also go here. So the structure is like a the structure is like this, this, CH3, 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 1, 2, 3, 4, 5, 6 hexamethyl benzene. So this is the reaction of your polymerization reaction. So all of the alkynes generally undergo polymerization, and they will produce suitable suitable aromatic organic compounds whenever they are passed through the red hot iron tube at approximately 600 degrees centigrade. Now we'll see the addition of ozone, or this is known as ozonolysis. Those who have not seen my classes, you can go to the ozonolysis and you'll see the ozonolysis of alkynes. Let us see. Okay, we have done it before. I'm just writing the reaction here. Alkynes are 1000 times less reactive towards ozone. So when ozonalized produces corresponding carboxylic acids. You can see here CH3, C, triple bond, C, single bond, CH3. If you can break here, you should make the carbon atoms which are with the triple bond, these two carbon atoms, you can make these two carbon atoms into COOH groups. COOH plus COOH single bond CH3. You should definitely see my previous videos and you will find out the ozonolysis, and you will see that all the alkynes generally when reacted with O3, or you can get the similar result when you treat the alkynes with KMNO4 alkaline. You should see here CH3, C triple bond, C single bond, CH3. You can give here alkaline KMNO4. This will give you CH3, COOH plus COOH single bond CH3. So these two reactions are actually the same. So you can use O3 ozone, or you can also use alkaline KMNO4 for the same purpose. So these are the ozonolysis of our alkynes. Now we have seen this linear catalyst. So we have seen this one also, CH3, C triple bond, C single bond CH3. When you give palladium oblique calcium carbonate in xylene, we have seen it. This is a linear catalyst. Always cis alkenes are formed. We have also seen this one is in our NCERT also. Always cis alkenes. What cis alkenes are formed? And we have also seen the Barth reduction, that CH3, C triple bond, C single bond, CH3, as we have given NaNH2 and ammonia. This will give us trans. So this is the linear reaction, linear catalyst reduction and Barth reduction. Now, now we'll see some aromatic electrophilic substitution reactions. Actually, this is also in your NCERT, and your Freadal Craft reaction is very important in nature. Now see here, most important Freadal Craft reactions. I am writing the first. I am writing the statement here. It's called as alkylation. It is actually an electrophilic aromatic substitution reaction in which alkyl or acyl groups can be attached with the ring. more than, sorry, other than alkyl and aryl groups, acyl groups, we can also add, actually it is substitution, also substitute hydrogens by halogens in presence of some Lewis acids such as AlCl3 or FeCl3. Now we are seeing the reactions, then we will see the mechanism, then we will see some important Friedel-Crafts reactions which are also asked in our entrance exams. Okay, so let us first start with Friedel-Crafts alkylation. Alkylation. When benzene is treated with alkyl halide with FeCl3 and AlCl3 gives alkylated benzene. As an example, when benzene is treated with methyl chloride with FeCl3 gives toluene as product. Gives toluene as product. Now you can see here. Now you can see here. I'm writing the reaction here. CH3Cl. This is the methyl chloride. AlCl3. This will give us toluene. So this is known as alkylation. Alkylation. Why alkylation? Alkyl group is added. Alkyl group. The mechanism is most important, and this will definitely be helpful to understand and to answer your entrance question papers. You can see here mechanism. CH3Cl plus your AlCl3 or FeCl3. Actually, it is Lewis acid. So this will do what? This will attract the Cl minus. It will have a CH3 plus AlCl4 minus. Now what happens? You can see here. This is benzene ring. The bond goes here. Whenever the bond goes to any of the carbon atom, this will get a minus charge. This will attract the plus charge here. And the structure will be hydrogen, CH3. Here is a plus charge. Actually, rest of the bonds will remain in the same position. Actually, what happens? This bond goes here. That's why here is a plus charge and here is a minus charge. The minus attracts the plus charge here and it will be attached. Now what happens? It was aromatic to maintain the aromaticity. AlCl4 comes near to it and extract the hydrogen and the bond goes to its initial position and the structure becomes like this. This is the toluene. This step is called re-aromatization. Re-aromatization. This is known as the re-aromatization procedure. So AlCl4 extract the hydrogen and the bond goes here. So you should only remember, you should always see the stability of the carbocation. Trademark point, most important point. I'll give you an example here. You should always see the stability of the carbocation. Those who have not seen my previous videos, you can definitely see those videos, because I'm now I will do some examples here which are definitely related to our previous videos, methyl shift, hydrate shift, etc. Now we are seeing some examples, classical examples here. At first, I'm having a example of your neat. When benzene is treated with, you should just see the stability of the carbocation. Okay, I'm giving you the shortcuts here. So whenever you give AlCl3, what happens? This Cl goes out. This Cl goes out with the AlCl3. Okay. So what happens? CH3, C, CH3, CH3, CH plus charge, single bond, CH3. Now what will you see? You should see the stability of this carbocation. This is secondary actually. So we should see that tertiary is more stable than secondary. So what happens, as we have done in our previous classes, you should remember those copy and see the copies. Methyl shift occurs. This is called 1,2 methyl shift. What happens? CH3, C plus charge, CH3, CH, CH3, CH3. So now the carbocation is 3 degree. Just join it. Just join it with benzene. With benzene. Just join the plus charge with the benzene. So what will be the structure here? You should see C, CH3, CH3, CH, CH3, CH3 is the major product and the stable product, and is the major quantity. So you should always see just the stability of the carbocation. Rest of the things you can forget here. Okay. You should always see the stability of the carbocation. I'm giving you another classical example here. You can give here AlCl3. Just remove this chlorine atom, hydrogen, here CH3, here CH plus charge, here CH3. You should always remember this one is secondary. I will get this hydrogen, and this will become plus charge, CH3, CH2, CH3. This is 3 degree. Just join it with the benzene ring. So the structure will be C, here CH3, here CH3, here CH2, and here CH3. So this is the product. So just join the plus charge with the benzene ring, that is which is the stable carbocation. You should always remember, you should always consider the stability of the carbocation. Let us see Freadal acylation. This was alkylation because alkyl group was added. Alkyl group was added. Now, acylation. Acylation means acyl groups are added. As an example, when benzene or benzene is treated with acetyl chloride, with AlCl3 gives acetophenone. You can see the structure and the mechanism here. The reaction mechanism is same. Here you can use a shortcut here, CH3COCl. There is no problem here actually. This is very simple. You can just remove the Cl minus and join this part with the benzene ring. So the structure will be COCH3. This is known as acetophenone. We'll see another one or two examples here. Another one or two examples here you can see here. Whenever you see this is a benzene ring, plus there is PH, C double bond O, single bond Cl, AlCl3. Just remove this Cl, join the rest of the part with the benzene. C double bond O, PH. This is known as benzoyl chloride. Always remember, this is sorry. This benzoyl chloride is this one. This is known as the benzophenone. Benzophenone. So these are the acylation reactions. Actually, acylation reaction is actually more easy than alkylation, because in case of alkylation, you should see the stability of the carbocation. But in case of acylation, there is no need to see the stability of your carbocation. You can just remove the halogen and add the rest of the part with the benzene ring. We are seeing some classical examples. Of Freadal craft. Question comes in our IIT exam that benzene is treated with CH2Cl2 in AlCl3. This is known as DCM or dichloromethane. The product is like that. How this is possible? You can see here CH2Cl, Cl. AlCl3 whenever reacts, this will have the Cl minus. So the structure becomes CH2 plus Cl. So as one carbocation, one carbon atom is present, you should directly join with your benzene. Whenever you is treated with benzene, will directly join with your benzene ring. This is known as the benzyl chloride. Now again, it reacts with AlCl3, gives this one CH2 plus charge. Again, whenever this is treated with benzene, you can directly add this group with benzene. So the structure will become diphenyl methane. Diphenyl methane is the structure here. So this is the special Freadal craft reaction. Again, you can see another special Freadal craft reaction here. When benzene is treated with chloroform, this will always give you triphenyl methane. The mechanism is same as before. So I am giving you another classical example, which was generally asked in a good examination. That's why exam we can see here. This is a special case. This is known as the intramolecular craft. You can see here. AlCl3. You cannot do this kind of reaction without the mechanism. So there is no shortcut here. I'm absolutely sorry for that. So I am extremely sorry because there is no shortcut here. You should know the mechanism. This kind of question is asked in a very important examinations. Okay. So this is the intramolecular Friedel-Crafts reaction. So we have done our Friedel-Crafts reaction. We'll see the same type of reaction of our nitration reaction. This is also in our NCRT. Nitration reaction is also very important. It plays an important role in our organic chemistry. Let us see the mechanism here. This is actually, this act as a acid, act as acid, this act as a base. Okay? Because H2SO4 is strong. Because H2SO4 is a strong acid. So if someone asks you what is the role of H2SO4 in the nitration, you should say that it is used as a strong acid here. So it will generate the NO2 plus, which is responsible for the nitration. Let us see the mechanism here. Always remember, whenever constant HNO3 and constant H2SO4 is given, you should always give nitrobenzene. You should always write down the product as nitrobenzene. So let us see the mechanism. HNO3, H2SO4, this gives NO2 plus. The reaction is as like as the Friedel-Crafts reaction, HSO4 minus. When you react with a benzene, as like as the Friedel-Crafts reaction, same actually. This will go here. So the structure will become, here is a plus charge, here hydrogen, here NO2, this HSO4 minus will have the H plus and the bond will become here. So this is the nitrobenzene. Nitrobenzene. A canary yellow crystal formed due to the nitration. This is called nitrobenzene. So this one is your nitrobenzene. So this is the mechanism. This is the nitration mechanism here. Actually, I want to write something here. Always remember, electron donating groups or groups that have plus I or plus R effects always activates the ring towards electrophilic substitutions such as Friedel-Crafts and nitration reactions. You can see here, whenever benzene is treated with concentrated HNO3, concentrated H2SO4, a mild heating 50 degrees centigrade is required to produce nitrobenzene. But when toluene is present, this is the toluene, and we know that this is an electron donating group. So whenever you give the same reaction at 25 degrees centigrade, the product is obtained. Two products will be obtained, CH3NO2 orthonitrotoluene and CH3 NO2 paranitrotoluene. So you should remember this one. Electron donating groups directs the electrophiles to the ortho and para position because they activate the ring. Okay. Okay. Now, 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 similarly, when EWGs are present, they deactivate the ring. So, if you want to do nitration here, you should give probably a high temperature of 2 degrees centigrade because it is an electron withdrawing group and it is a minus I or minus R effect, deactivates the ring. And always remember, you should write down, always remember meta isomers is possible, meta isomer, because so they direct the electrophile to the meta position. It is known as meta dinitrobenzene. You can see here, if there is an electron donating group here, CH3, you can do the nitration at 25 degrees centigrade. You can see the temperature difference here. It is 100 degree and then 25 degree. This will produce orthoisomers and para-isomers as product. NO2, CH3, NO2 para-isomer is also possible. So you should remember this one. Electron donating group has plus I and plus R effect. They direct the electrophile towards the ortho and para position. But in case of meta isomers, in case of electron withdrawing groups, they direct the groups to the meta position. Okay, so they will deactivate the ring, and the reaction is difficult. You should always remember here that nitrobenzene star point, nitrobenzene never undergo Freadal reaction. Okay, I'm ending this video here. In the tomorrow's class, we will see the conversions. Okay, so in organic chemistry, everything depends upon conversion, because whenever you can do the conversion, you will see how to remember the reagents and how to apply them. So this is the end of our theory in case of our hydrocarbon actually, but the chapter is not actually over, because we will do some conversions and we will do some question papers from MS Chauhan and Himanshu Pandey also. So let us wind up this video here. Thank you for watching, and thank you for staying with us. Thank you.